Alright, so I have 4 minus 4, which is 0, so this term just goes away. I'm really left with 1 times 12 minus 14, or negative 2.
Yep. Sorry.
Thank you very much.
Yeah. Double-sided, is that a problem?
Nope, that's fine. Thank you. Alright, so that's my determinant for this matrix. Any questions about that calculation? So walking it through, I saw kind of a variety of answers. So you'll make sure that if you didn't get to negative 2, you find the little math mistake along the way, and it's not something more fundamental. Little mistakes are, well, I took 12 minus 14 and I called it positive 2 or something. Bigger mistakes are forgetting this minus sign, right, which is kind of part of the equation. It's fundamental. Okay. Now, there's actually other ways we can calculate this thing. Kind of the end of class yesterday, we talked about how row operations will affect the value of the determinant, and we can use those to calculate a determinant if we want. So, in other words, this determinant should be related to the determinant of, well, if I take A and I do some row operations, it might or might not affect the determinant value. Certain operations do, certain don't. If I switch rows, does that affect the value of the determinant? It does. That will change the sign of the determinant, right? It'll make it a negative. If I add 2 of one row to the next row, does that change the value? That does not. And if I scale it, that does also change the value. So in other words, if I just take, if I do the first couple row operations, if I take row 2 minus 3 of row 1, should that affect my determinant? So the determinant will be the same of this original matrix, or if I take 1, 2, 1, and then 3 minus 1 is 0, 7 minus 3 times 2 is 1, 3 minus 3 times 1 is 0. So if I just make that row operation, I shouldn't have affected the value of my determinant. If I do another one, if I take the third row and subtract 2 of the first row, that also shouldn't change anything. That would be 2 minus 2 times 1, 4 minus 2 times 2, and 0 minus 2 times 1. So because those specific row operations don't change the value of the determinant A should be equal to the determinant of this matrix. And why is that useful? Yep, the diagonals, absolutely. It's a triangular matrix, so the determinant is just the product of the diagonal, just 1 times negative 2. So from here I can see directly it's negative 2. All right, any questions about that? Okay. I do want to go through a little more about the LU factorization real quick just to kind of relate it to this specific calculation. I haven't quite posted that extra credit assignment. It's going to be almost exactly like the inverse matrix one that I posted. So it's going to have you construct a couple of elementary matrices and just show how to get the LU factorization. But to kind of talk about that, let's just think about this matrix in terms of those row operations that we just did. So basically, I took my matrix A, which was 1, 2, 1, 3, 7, 3, 2, 4, 0. I did a couple row operations to it. My first row operation was to take row 2 and subtract 3 of row 1. I can get that same effect by multiplying that matrix by this thing. That's the elementary matrix, where if I take the product of these two, the result will essentially be A with that one row operation done. Does that make sense? Okay. So the result of this thing will be, what did I have here? 1, 2, 1, and then 0, 1, 0, 2, 4, 0. That's like a result of that first row operation. If I take that matrix and do the other row operation, I'd take row 3 and subtract 2 of row 1. That's that row operation. The result will be this thing. The result will be the matrix 1, 2, 1, 0, 1, 0, 0, 0, negative 2. Like that. Any questions about that expression? It says do these two row operations and basically you get to here. And I like to make it that far because over here I have an upper triangular matrix. On the left-hand side, I've done two elementary row operations. And the nice thing about those elementary matrices is they are definitely invertible. How can I justify that? Why does it make sense that they're invertible? Think of inverse operation. Does it make sense there should be an inverse to a row operation matrix?
And the position of each column.
Absolutely, we can definitely look at that. I mean, if I look at any one of these, if I were to row reduce it, I would have a pivot position in every row and column. Now, I would have to do a little work to show that, right? I have to do the row reduction. So another way to think about it is I think of an inverse operation. The whole idea of this matrix here is to take row 3 and subtract 2 of row 1. Well, what's the opposite of that? Adding 2 of row 1. Right, so it's very easy for me to take this thing and go back to identity. All I do is take identity, use one row operation to get to here. If I do one row operation, I'll get back to identity. And that's part of being invertibles. Can you row reduce to identity? Well, clearly I can row reduce to identity if I just came from identity with one step. Right? Okay, so what I'm going to do is I'm going to call these some things. I'm going to call this E2, some elementary row operation. And I basically multiply both sides by the inverse of E2. All right, if I take the inverse of E2 over here and the inverse of E2 over here, what's going to happen to these two? They're going to go away, right? Because that's going to be identity. And once those go away, I'm going to multiply again by the inverse of E1. And over here, the inverse of E1. All right, so once those cancel, I'll be left with just these two. What's going to happen to them two? Well, it's going to be identity, and those are going to go away as well. The result is going to be A equal to E inverse of E1. Well, I know what the inverse of E1 is. Instead of subtracting 3, I'm just going to add 3 to that position. That's the inverse operation. Inverse of E2. That's going to be, well, instead of subtracting, I'm going to add those values there. And then I have the result that I got. And then as a last step, I'm going to say, well, all this matrix does is take R2 and add 3 of R1 to it. So it's easy enough for me to actually do that row operation on this matrix. So I'm going to multiply those two essentially. The result will be this. And this is the LU factorization, because now I have a lower triangular and an upper triangular. Now, that seemed like a lot of work kind of to do that, right? But in reality, it's not. If you wrote a program to do this, all you're doing is collecting the row operations as you get to a upper echelon triangle. It's kind of what we did to find the inverse. We just gathered up all the row operations to get to identity. Here we're just not going all the way. Here we're just stopping early. Instead of going all the way to identity, we're just stopping whenever we get to a nice row echelon form instead of reduced row echelon form. We just stop there. We still collect up our row operations. The only difference now is we have to invert them. But once again, it's easy to kind of invert elementary matrices, so that doesn't cost us anything computing-wise. So a common practice in computer land is to take A and get to this factorization, because it's easier to use this than it is to use an inverse matrix. It's also very easy to compute the determinant of this, because the determinant of this product is just the product of individual determinants. And what's the determinant of this one? What's the determinant of L?
1.
1, right? Because it's lower triangular, so it's the product of diagonals. What's the determinant of U?
-2.
-2. So, of course, the determinant of the product is 1 times -2, which is -2, which is, of course, what we got above as well. So this is a very computationally useful factorization. There's actually lots of other factorizations that we do on matrices that you'll learn about later on. All right, so the extra credit is going to look like find the E1, E2 to do the row that will do this reduction, and then invert them, multiply them together, and show that that's the LU decomposition. Once again, I'll write that up later today. Any questions from the warm-up? All right, we're going to do a couple more real quick here. Find these determinants. Gotta get a little work in this morning here. The blood flowing. Talk too long, I see the drifting. Some writing here. Once again, get started on these and then try to look for some tricks. Try to look for those simplifications. But you're going to have to do some of these on exams. And if you have to take every determinant and use the formula, you're going to run out of time. Right, so you need to see the tricks. All right, I decided to expand down the first column. I have 1 times that subdeterminant times a bunch of zeros, or plus a bunch of zeros. So this looks like 1 times 2 minus 4, looks like negative 2. Now I go to the next one, and of course I could kind of do the same calculation here, but in this case I don't need to. And once again, we want to look for these properties, because in this case it doesn't really matter. It'd be about as much work to calculate this one too. But in a larger problem, you want to make use of these properties. The only difference between the first matrix and the second matrix is what? Absolutely, that R2 is divided by 2. So essentially this should be 1/2 of the last determinant. So all I've done is taken the one row from A and divided it by 2. Once I already calculated that last determinant, this should be 1/2 of negative 2, it should be negative 1. And of course, if you wanted to, you could have said 1 times the subdeterminant like this, and this would have been 1 minus 2, which would also be negative 1. Once again, looking for those properties is going to be useful for larger problems. What about the next one? How did I go from this matrix to this matrix?
Subtract R2 from R3.
Yep, absolutely. It was just a subtraction of rows here. Does that affect the value of the determinant? It doesn't, so this one will be the same. That one doesn't change at all. And of course, for that one, because it's upper triangular, we could have just looked at the diagonals as well. Once again, seeing those row operations and how they affect the determinant is an important property. Any questions about those? You got to be a little bit careful about the scaling one, because your book just writes it a little bit weird, right? It says if you go from A to B, the determinant of B is scaled by this, so sometimes it can lead you to multiply the wrong value. So just be careful whether you're multiplying or dividing. All right. Last thing I want to talk about with respect to determinants is the application. They're just everywhere, right? And sometimes I look at them and I say, I don't even know why they're in all these different areas. They just come up. So they're really a broad thing. They seem like a weird calculation, and we kind of see why did they came up with the weird calculation. They came up specifically to determine whether or not an inverse exists. But they just show up in the weirdest spots. For instance, in Calculus 3, right, they're part of a calculation for something called the Jacobian. And we see them when we do change of variables in multi-value variable functions. So if you want to do an integral of a function of 2 variables, and you want to change variables from cylindrical to spherical, there's this weird factor that you have to kick in there. And that factor can be calculated by doing a Jacobian of the change of variables. So as you change the variables, that thing will pop up. That's also the way we calculate cross products. So if I take the cross product of 2 vectors, U cross V, I'll go I, J, K, and I write in my vector values here. And I can do the calculation like it's a determinant of some special matrix. So it's almost a mnemonic to do this calculation, which also seems kind of weird. It tells us about area and volume in 2 and 3 dimensions. So if I have two vectors like this, I calculate the magnitude of their cross product by using this determinant calculation, it will give me the area of that parallelogram. Weird. And of course you can show all these, and some of them are pretty easy to prove, but it's just some other use of the determinant here. And that will extend into higher dimensions if we keep the idea of determinant. Also, we can think about it generally as a mapping. It's basically assigning a number value to a matrix. And that's going to be a useful thing. As we go back and do calculus 3 stuff, where you're creating these matrices of functions, right, and the derivative values, you want a number value. You do something like the second derivative test, you want to say, hey, what's the number associated to this thing? Well, how do you assign a number value to a matrix thing? You figure the determinant. That's kind of what it's doing. It's giving a number value to it. And of course, fundamentally, the reason we came up with this calculation is because it was exactly what we needed to show whether an inverse exists. And the last one I've listed here, although there are lots of others, we're going to use it to solve the eigenvalue equation, which is the beginning of chapter 5. The determinant is going to be a calculation along that road. So determinants just come up a lot. And that leads us to chapter 5, eigenvalues and eigenvectors. I would say most would say this is the most difficult chapter for linear algebra. So we're going to kind of work ahead fast and then build in a couple days where we can just review and kind of go through and answer questions and work on some problems. That's going to be the plan here. All right, so today we'll talk about what are eigenvalues and eigenvectors. How do we calculate them? Look at some properties. We probably won't get into similar transformations. In the history stuff, we'll kind of blend in a little bit here and there. The historical stuff I'm going to bring up is going to be related to different fields, so don't worry, that's not going to be testable. If you're in Calc 3, some of it might be interesting, or if you've had some other classes that might be more relevant. Also going to kind of foreshadow some things you're going to be doing in differential equations. How many people are going on to differential equations? A few. Okay. Most people take that right after this course, and you'll see why they're so connected as you get into differential equations. You have to calculate a lot of this stuff. All right, any questions about what we want to do today? Okay. Eigenvalues, eigenvectors. Here's what they are. An eigenvector, now the n by n matrix, so that's a square matrix, n by n, is a non-zero, double underline because the eigenvectors must be non-zero, vector x, such that the matrix A times x is equal to the scalar lambda, that's the Greek lambda, for some scalar lambda called the eigenvalue. So, eigenvalues and eigenvector. And it's just a vector and a scalar that satisfy this equation. That's all they are. Now, why that equation? Let's look at an example real quick here. If I have the matrix A, for instance, and I have the vector x, for instance, and I multiply those two things together, what do I get? Should multiply them real quick for me. What's the result here? Zero 12. Okay. I say, hey, wait a second, that looks kind of like x. In fact, it turns out it's just 3 times x. So the effect of multiplying that vector by this matrix is really the same effect as just taking it and multiplying by a number. That's actually kind of a special thing. I mean, graphically, we've seen before that if I have some vectors and I multiply them by matrices, I can do reflections, rotations, different shifts. It takes that vector and transforms it into some other vector in R2. Now what this is saying is this is a special vector related to this matrix that's associated with a special value that just takes our vector and scales it. It's just a scaling of our original vector. That's kind of why they have the name eigenvalue and eigenvector. Eigen is actually a German word, and it's kind of like saying same vector. If you look at Wikipedia, it has about 8 other different translations, but it's saying you take the vector and you're getting a same kind of vector from it. You're just scaling it. Okay? So when I get a little bored, I might try the German Eigen. I give it a good accent when you try to say it here. Okay. But it's a good way to remember this equation. Right? It's just a scaling of the original vector. So think about that geometric description. Just multiplying by a scalar. Okay. So now we know what they are. How do we calculate them? Well, it's kind of a pain here, right? We have a matrix A. We have to find lambda. We have to find x. Essentially, we have 2 variables in one equation. Right? That's a problem. If I have 2 variables, I need 2 equations to solve them. So I got to generate another equation, essentially, to solve this thing. So I'm going to do a little bit of algebra to this thing. I'm going to subtract lambda x to the other side. I'll get my 0 vector over here. I'm going to factor an x out, being a little bit careful. Remember, this is matrix vector multiplication, so the order matters. It's going to look like this. And there you might have a little question like, hey, where did I come from? Where did that identity matrix come from? It kind of makes sense where it comes from if you just write it all out. So kind of as an example, let's just do what we had before. 2, 0, 0, 3. I'm going to put an x1 in here, saying that's equal to some number times x1, x2. Right, when I subtract them over, that looks like this. x1, x2, minus lambda x1, x2 equals my 0 vector. And now I jump to this thing. Well, what is this thing? Well, if I kind of break that down here, lambda times an identity matrix would look like this. And if I multiplied through, I would get lambda and lambda, right, if I actually did the multiplication. And if I take that matrix and multiply it by this vector, well, I'll be left with lambda x1, lambda x2, which is the same thing as lambda times the vector. Okay, so all I've done was taken lambda x here and kind of factored out the x, but because I'm dealing with matrices and vectors and the dimensions are different, that identity kind of gets built in. Okay, but you can show, kind of do that calculation, that lambda I times x is the same thing as lambda x. Okay. You could justify it a couple other ways as well. I could just say I times x is x, and that would also work. But I have to include that I when I factor it out to make the dimensions correct. Okay. So I get to this thing. Up here we'll write that out as well. 2, 0, 0, 3 minus lambda times identity. I'll just write in identity here. All that times x1, x2. And then I can actually calculate this thing here. If I do that calculation, the result is 2 minus lambda, 0, 0, 3 minus lambda. And the reason I want to show that is because this looks kind of weird and ugly, but this thing is just A where I subtract lambda on the diagonals. That's all it is. Because think about what the operation does. It takes an identity times lambda. That puts a lambda all along the diagonals. When I subtract 2 matrices, all it's doing is subtracting component-wise, subtracting lambdas on the diagonals and zeros everywhere else. And so this is just a matrix. So really I have matrix times x equals 0. Now, that's just rearranging it. I still only have one equation. But now I'm going to look at that and say, you know what? This thing right here, this matrix, whatever it is, it cannot be invertible. Why not? Why can't this be invertible? Should talk about it in groups here. Just kind of turn to your neighbor and say, why can't that be invertible? And see if you guys can come up with something. What would it mean for it to be invertible? What would happen to it be invertible? There was an inverse. What's the inverse for it? Sometimes the notation makes it confusing. Let's call it B. Call that matrix B. Now I have Bx equals 0. If there was an inverse, oh, that'd be great. I could just take B inverse times both sides. What would I get over here? If I took B inverse times B times x, what would I get on this side? Just x. If I took B inverse times this, what would I get? What would that tell me about x? Can x be 0? Non-zero. Non-zero x for eigenvectors. Okay, so if I'm looking for non-zero x here, it can't be invertible. I mean, when we get to this point, we're basically saying, okay, eigenvectors are just the solutions to this homogeneous equation. Are there solutions to this homogeneous equation? There's always solutions, right? There's always a trivial solution, but we're bored with that. Of course we know that x equals 0 satisfies this. That's trivial. Something times 0 equals something times 0. Hooray. And we can always do that. So the point is we're looking for non-zero things. The only way there's non-zero things are if this thing is not invertible. Okay, so that thing can't be invertible. Wait a second. If it's not invertible, I know something about its determinant. If it's not invertible, what does that tell me about its determinant?
It's equal to 0.
It's equal to 0. Okay, so knowing that theory about the fact that this thing can't be invertible and the determinant is equal to 0 for matrices that are not invertible, says that another equation would be this. That's great, because now I've generated another equation, and not only have I generated another equation, but this equation doesn't have any x's in it. So I can just take this thing and solve it for lambda. Okay. But it's that thought process that's really important. I mean, I can give you the mechanical steps. You take a matrix A, you solve this equation for lambda. Once you find your lambda, you plug it in here, solve it for x. That's what we're going to do later. But understanding why, I think, is very important. The idea is that we start off with this thing. It's easy enough for us to get this homogeneous equation. We're looking for non-trivial solutions to this thing. There are only non-trivial solutions if the determinant of this thing is 0. If this thing is not invertible. That gives us this equation. It also kind of warns us ahead of time about what kind of solutions we're going to get. When we solve this thing, we're going to get infinitely many solutions. Right? Because we're going to choose this specifically so this is not invertible. So there are other solutions. So there are non-trivial solutions, which means there are infinitely many solutions here. Okay? All right, so that's what we got to do. So let me clean up this side over here. Basically, we have to take this thing first. We're going to use this thing to find the eigenvalues, to find the lambdas. Okay, so we started with A equals 2, 0, 0, 3. So this thing is just a matrix. This thing is just a matrix where we have 2 minus lambda, 0, 0, 3 minus lambda. And we're saying, when is that thing equal to 0? This is a really nice case. It's going to be more complicated in future cases. But for this one, if I calculate that determinant, it's going to look like 2 minus lambda times 3 minus lambda. It's the product of the diagonals. I'm saying when is that equal to 0? Now in general, once again, this could be bigger, 20 by 20. This could be lots of fun.
Sure.
But also there could be other values here, which means we have to calculate this determinant the long way, which makes it actually quite a bit harder. Because if I have other values here, I'll get other numbers here. I'll have to expand everything out. When I expand this out, what's going to turn into? What kind of equation is this going to be? It'll be a polynomial. In this case, it's going to be a second-degree polynomial. I'm going to get a quadratic thing here. And in general, I'll have to find the roots. The roots will be the values of lambda. The nice thing here is that I can see the roots. What are the root values? What are my solutions? Lambda equals 2 and lambda equals 3. It's like, when is this thing equal to 0? Well, it's equal to 0 when this thing is 0 or when this thing is 0. Those are our two options. So I'll have two values here. So my solutions are lambda equals 2 and lambda equals 3. I have two eigenvalues. So that was step 1. Use that determinant equation to find the eigenvalues. Now for each eigenvalue, we have to find the associated eigenvector. So 2, use the lambdas in a minus lambda I into the homogeneous equation now to find the eigenvectors. So I say, when lambda equals 2, I'll do that case first. I basically have a minus 2 times identity times x equals 0. And I'm just trying to find those solutions. Well, once again, a minus 2i, this is that equation right here, right? This is that matrix. So I'm just basically plugging in lambda equals 2 into that matrix. And basically this thing is just 0, 0, 0, 1 in this case. Right? All I did was plug in lambda equals 2. Now, of course, I could write that as an augmented system, but I don't need to because the right-hand side is just 0. Right? So all I'd do is moving zeros around. And I could actually tweak this a little bit, but it's in a good enough form where I can just go right to the equations in this case. If I want to write the solutions to this, I take my matrix, I do whatever reduction I need to do, and then I write out the equations, and I write my solution in parametric form. And that'll give me a nice clean solution. So what are my equations from this one? I need an x1 equals and an x2 equals. What are the linear system I get from this matrix equation? First equation would say 0 times x1 plus 0 times x2 equals 0. That's about useless. What does the second equation tell me? A little louder, what was it? x2 equals 0. Okay, great, I got that one. Am I going to get an equation for x1? Why not? It's a free variable, so x1 is just x1. Okay? Now I'm going to write this out as a parametric solution. My solution is a vector with x1 and x2 as components. x1 is just x1. x2 is just 0. Now I can see my parametric form. There's my parametric form for this solution. And this tells me a lot about what I'm doing here. I'm not really just finding an eigenvector, because I know there's actually going to be infinitely many eigenvectors. Remember, I'm looking for non-trivial solutions to this thing. So I know there's going to be infinitely many solutions. I'm not really finding an eigenvector so much as I'm finding a basis for the space of all eigenvectors. All right, if I think about my solutions to this thing, to find the solutions to ax equals 0, well, the set of all solutions to that is going to be the null space. And so the result here is going to be a subspace of R2. Now, because I'm talking about eigenvectors, we're going to give this thing a name. It's going to be the eigenspace. The eigenspace is going to be all the eigenvectors plus the 0 vector. Why do I have to say it like that? Why do I have to say that the eigenspace is the set of all eigenvectors plus the zero vector?
Space has to contain zero vector.
Absolutely, and 0 is not an eigenvector. Right? So I kind of include that separately to complete the space. So x1, any number times 1, 0, is going to be the eigenspace associated with the eigenvalue lambda equals 2. A basis for that eigenspace is the vector 1, 0. Or the basis could be 2, 0. Right? It doesn't really matter which one I pick. I can pick one. Right? Call that my. So I'll talk about eigenvalues and their associated eigenvectors. And so I'll talk about finding the eigenvector. But we all need to understand that when I say find the eigenvector, we're really saying find a basis for that eigenspace. Okay? And by the way, the real great thing about that is grading. Because you can write 1, 0, and you can write 22, 0, and you can write 33, 0, and they're all going to be correct. And not too bad to see in this case, but when they're bigger problems, you guys can be pretty tricky on how you want to scale things to see if I'm paying attention. So it can be a little challenging to grade. Okay, now that's just 1. Now we got to go back and do lambda equals 3. So we go back to lambda equals 3. We plug in that value into our a minus lambda I thing. Here I'll get negative 1, 0, 0, 0. I expect to have a free variable because I expect to have infinitely many solutions. When I write this one out, it says, well, let's see, it says negative x1 equals 0, so x1 equals 0. And it looks like x2 is my free variable. So this time my solution is x2, 0, or 0, 1. So this is the other eigenvector. That's the eigenvector associated with lambda equals 3. Now I'll tell you that these turn out to be really nice eigenvectors because that was a really nice matrix we started with. We started with this beautiful diagonal matrix, so we get beautiful eigenvectors. All was right with the world. So what I want to stress here is the process. First, we find the eigenvalues using the determinant equation. And then for each one of those eigenvalues, we have to plug them into the homogeneous equation to find the associated eigenvectors. All right, that's what we'll summarize here. So that's a summary of the formal process. Oh, you should just stretch out a little bit because you know what's coming next, right? Any questions about that first example or this process? And with all these things, I always suggest you just kind of rephrase them in your own words if you feel that's easier. It doesn't make any sense for you to write down how I'm summarizing things. It doesn't make any sense to you. Always go back and re-summarize. All right, so first we find the eigenvalues, the determinant equation. Then we use those to find the eigenvectors. All right, your turn. Oh, you see that last one? Like that. All right, try it for this one. Eigenvalues, eigenvectors. Right? Once you get started, I want you to find the eigenvalues. I want you to take one of the eigenvalues and find the eigenvector. I'm telling you one because I'm not going to do them all in class either, so it's a long process, but we'll do one of them. Feel free to work in groups. If you get stuck, feel free to ask. process is a little bit confusing, but it's very mechanical. So the trick is to do 100 of these every night. So we have to do this equation first. So what is A? What is lambda? How do we do that subtraction? Just some variable. Call it a parameter and just put a lambda in there. And that's the thing we're solving for. So lambda is just some number. What's I? Okay, so minus some number times identity. Yep. Good. Yep. And what is lambda times that matrix? What does that do? Okay, I'll just put lambdas here. Yes. What happens when you subtract those two matrices? Or there's these brackets, right? So if you multiply these two, all that subtraction will do is really, because this minus 0 is the same, this minus 0 is the same. So all it really did is this thing. So we just subtract it out of the bag. So that's all this A minus lambda I thing is. It's just A with a lambda on the diagonal, subtracting one. Yes. And that's the determinant. They're not zeros, though. These are and that's the determinant we have to take. Okay. All right, so let's just make sure we're all starting at the same spot here. This is our first calculation. That A minus lambda I, the effect of that is just to subtract lambda on the diagonals. So we're calculating this determinant. The question is, when is that thing equal to 0? I'm going to get another polynomial from this, but it could be a third degree polynomial in this case. So we have to find the roots of that when we're all done. So it's a lot of algebra, but that's where we're starting with. Okay? That's what we need to start with.
Nobody wants to do it?
Yeah, that's right.
I don't want It might not be.
Yeah, that 4 is not there.
That's gone.
4?
Yeah, it's gone. That's
No, that's part of it. You're going to determine that you can expand on any column or row.
Oh.
It's not going to be that pretty, but it's going to be a little bit of algebra.
Oh, I know. You use
Don't blow my mind like that.
All right, so let's do this determinant calculation and see what we're going to get for one of these vectors. All right, so I'm going to expand along the third row. I'm going to put my signs down here. I got plus, minus, plus, minus, plus, minus, plus, minus, plus. So I have a plus in the last term. It's going to be 0 plus some stuff, 0 plus some stuff, and the last term is going to be 1 minus lambda times a little subdeterminant, where I have 7 minus lambda, negative 4, 4, and negative 3 minus lambda. Now I'm going to finish that calculation. 1 minus lambda times 7 minus lambda, negative 3 minus lambda, minus a negative 16. Having those values on the diagonal makes it much harder, right? Because now I can't say this is equal to 0 when those three things are equal to 0. I have to actually write this out now. So what I'm going to do is I'm going to do that multiplication, so add the 16, I'll have a quadratic thing in there, and then I'll have to try to factor the quadratic, or use the quadratic formula. That's all part of this problem. So I got 1 minus lambda. I do the multiplication here. I'm going to get negative 21 minus 7 lambda plus 3 lambda plus lambda squared. I'll add the 16 to that. I'll reorganize. I'll get lambda squared minus 4 lambda and minus 5. Now I look at that quadratic, I try to factor it. What do I got for a factored form? It looks like I can go lambda minus 5, lambda plus 1. So now I've factored everything, and the question is, when is that equal to 0? And now because I've fully factored it, I can see my roots are going to be lambda equals 1, negative 1, and 5. Good times, right. That's all one part of this much bigger problem now. All this quadratic stuff, algebra, polynomials, all that kind of stuff. Now notice, if I would expand this all out, I would get a third degree. That's because I'm starting with a 3 by 3. If I started with a 10 by 10, I would get a 10th degree thing. Do I have a formula for 10 degree things? There is no formula for a 10th degree. There is a formula for a cubics. It's complicated. And I believe you can get someone to the 4th degree. But anything above quintic, there is no formula to find the roots. You have to use numerical techniques. So this brings up a difficulty of finding these eigenvalues and eigenvectors. It's a real problem. Now I have my eigenvalues. I choose one. If I choose lambda equals 1, I'll find that associated eigenvector. I plug in lambda equals 1 into that thing. I will get 6 minus 4 minus 6, 4 minus 4 minus 4, 0, 0, and 0. Now I have to grab that thing and do the row reduction. Because I'm already out of time, I'm going to tell you that the row reduction turns out to be 1, 0, negative 7 halves, 0, 1, negative 5 halves, 0, 0, 0. After the row reduced form, I would grab that thing. You don't have to write this down. I really encourage you to go through this, kind of verify all this work yourself. This says x1 minus 7 halves x3 equals 0, x2 minus 5 halves x3 equals 0, and x3 is my free variable. So then I write that into my big form here. I'll have x3 is x3, x2 is, if I add this to the other side, I'll get this thing. I'll add this thing to the other side to get that. So the eigenvector is 7 halves, 5 halves, and 1. And so I write my solution as lambda equals 1, and my eigenvector is, well, I don't like that. I'm going to write 7, 5, and 2. Because I can. Because any multiple of my eigenvector is also an eigenvector, and I don't want to carry those fractions around. I don't want to grade them either, so please do that. Okay? All right, but we can put it into a nice form, so that's what you want to do. So that's the eigenvalue, that's the eigenvector. Now we repeat with the other two eigenvalues, and that's this one problem. Okay? So these are going to be long, so work through these mechanics because we have a lot of theory to talk about in class related to eigenvectors. So next class we're going to try to get through 5.2 and 5.3. We'll get started on that. So make sure you kind of preview those sections. We'll talk about similarity transforms and some other properties of eigenvectors. That's all I got for today.